What's up, everybody? Welcome to another video, and I hope you're ready to flex those brain muscles. This is part 2 of my Precalculus final exam review series. So if you missed part 1, click right up here. A little link will pop down. This is part 2. That means we're getting into trigonometry. So this video will basically be a bunch of trig, radians, degrees, finding exact values of trig expressions, some arc length, area of a sector, some graphing, all that stuff. But if you want to see for yourself, click the link in the description below. That's where you'll find this awesome little packet that I made myself. And this is what I'll be going through in this video. I'll be going through this packet. But let me just warn you, it's not going to help you that much to just print it out and follow along with me. What's really going to help you is to print it out and think about some of these problems on your own. Try to see if you can go through this worksheet. It's only 7 problems. See if you can go through it and then use this video to fill in those gaps in your understanding. Use this video to sort of check your answers, right? That's how you're really going to learn. That's how this video is really going to benefit you, and that is the intention of these review videos that I make, is just to be a review, right? So I will move a little bit quicker than I maybe normally would in a full instructional video where I break everything down. But if I move a little bit too fast for you, then you can go check out my pre-cal playlist where I do have instructional videos where I break everything down real slow. And throughout the video, I'll be linking them. It'll pop down when I talk about a certain topic, and you can click and go watch that kind of thing. So I hope you all enjoyed this video. If you do, like, subscribe, leave a comment below letting me know that you appreciate this. I appreciate you appreciating me. But anyway, let's get to it. So for number 1, we are given these 2 angles in degrees and asked to convert them to radians. So this is actually pretty simple. We just multiply by pi over 180. Okay, so I'm going to take this 120 degrees and multiply that by pi over 180. And once I simplify this, it will be in radians. And where this pi over 180 comes from is the fact that 2 pi radians equals 360 degrees. We do some manipulating and we get that 1 degree equals pi over 180 radians. Therefore, 120 degrees equals 120 times pi over 180 radians. I break this down fully in a video that I'll link right up here. So once we simplify this, let's see, 60 is a common factor between these two. 60 times 2 gives us 120, so we have a 2 pi in the numerator. 60 times 3 gives us 180, so we get 2 pi over 3 for part A. For part B, same thing, times pi over 180. So we're definitely going to have pi in the numerator. Let's see, 195 and 180. I think a common factor will be 15. 15 goes into 195 13 times. And for 180, it's 12. So we're left with 13 pi over 12. I did that a little bit fast. If it took you a little longer, that's fine. Maybe you divide these both by 5 first, and then you do the factor of 3, right? Maybe it's a process for you. For me, I just jump straight to it. Here we go. Radians, radians. All right, so for number 2, we're doing another conversion. This time we're converting these angles from radians to degrees. So instead of multiplying by pi over 180, we're going to multiply by 180 over pi. And again, this just comes from the fact that 2 pi radians equals 360 degrees. We do some manipulating and we realize that 1 radian is equal to 180 over pi degrees. So therefore, 3 pi over 4 radians is equal to 3 pi over 4 times 180 over pi degrees. And the way I kind of remember this too, because I sometimes forget, is it 180 over pi, is it pi over 180? When we're going from radians to degrees, typically the pi disappears, right? Not always. I'm not saying that degree measures can't have pi in them, but usually they don't. So to cancel that pi, we need it in the bottom. That's one way I remember, but whatever works for you. So these pi's will cancel. Pi's go by. 4 into 180, that gives me what, 45? Yep, I think that does. So I'm left with 3 times 45 in the numerator. 135 degrees. And again, I'm doing this a little bit fast. I trust that you can do this simplifying on your own. If it takes you a little longer, that's okay. So I'm going to do the same thing here. Times 180 over pi. Pi's go by. 3 goes into 180. That becomes 60. That becomes 60 there. Negative. The negative just hangs out. Doesn't really do anything different for us. We just let it chill there. So negative 2 times 60, negative 120 degrees. And that's that. Degrees, degrees. All right, so for number 3, we're going to find the exact value of some different trig expressions. And the way I go about this is I first draw the angle, I determine what quadrant I'm in and find a reference angle if I need to, and then I get the exact value from that information, from the quadrant and the reference angle. That's the way I do it. If you do it a little differently, that's okay, as long as you get to the same answer and as long as you feel comfortable finding these exact values, because this will be important moving forward. You will need to know how to do this for sure. So let's go and jump into it. 3 pi over 2, I can draw that. let's see, pi over 2, pi, 3 pi over 2. So it's actually down here on the y-axis. This is what I call a quadrantal angle. It's on one of the axes, and I think these are really easy to deal with because our r is 1, our y in this case is -1. This is y over r. That's -1/1. It's that simple, right? So these you don't have to really memorize anything. Here, cosine is what? 0, because x is 0, right? Pretty easy to find these angles in my opinion. So there we go. Sine of 3 pi over 2 is -1. Let's go to part B. Cosine 7 pi over 4. I can draw this for sure. It's going to wrap all the way around here into the 4th quadrant. And if it takes you a little bit longer to picture this or draw it, that's okay. If it takes you a little longer, that's fine as long as you can do it. So here we're in the 1, 2, 3, 4th quadrant. So our answer is going to be positive, right? Because we're dealing with cosine. Cosine is positive in the 1st and 4th quadrants. And we have a reference angle of pi over 4. So that means the cosine of 7 pi over 4 is actually equal to the cosine of pi over 4, right? Cosine of pi over 4 is √2/2, so bam, √2/2. So how I do it, again, I have a few values memorized. I have basically these first quadrant angles memorized, and based on the reference angle and the quadrant location, I'm able to match these up with these common values of 1/2, √2/2, and √3/2. That's just how I do it. Tangent, 2 pi over 3. Let's see, I can draw that for sure. 2 pi over 3, I think it's going to be right about there. In the 2nd quadrant, we're dealing with tangent, so whatever our answer is, it's going to be negative, right? Negative, because we're 2nd quadrant. Let's see, our reference angle is pi over 3. It's going to be negative. So we can actually write this equals what? I can rewrite it as sine and cosine if that's easier. But I know that since it's negative and we have a reference angle of pi over 3, I believe that is √3. So it's going to be -√3. But if you didn't know that, if you don't have that memorized, what you could have done is what? Well, you could have rewrote it as, well, this is sine of 2 pi over 3 over cosine of 2 pi over 3, and then done it that way. Found each of these, that's fine as well. You could have also noticed that, well, this is going to be the negative of sine of pi over 3 over cosine pi over 3. That works as well. Whatever way you want to do it. There's a bunch of different ways to go about these, but -√3 should be the correct answer. All right, so we got a few more examples of finding exact values. And with these kind of examples, I'm really going to take advantage of those reciprocal identities. And what I mean by that is, I know that secant is the reciprocal of cosine, and I know that cosecant is the reciprocal of sine. So knowing that, I can just find cosine of -3 pi over 4 and flip it. And that's going to be the same thing as the secant of -3 pi over 4. Similarly, I can just find the sine of 11 pi over 6 and flip it. And that's going to be the cosecant of 11 pi over 6. So there's no reason to be intimidated. I see a lot of students are scared of secant and cosecant. There's no reason to be. We can always rewrite stuff in terms of sine and cosine. Even with cotangent, we can write as cosine over sine. So if you're at least comfortable with sine and cosine, then you can find whatever it is you need to find. Just a quick reminder on that. So that's really the approach I'm going to take. But I'm still going to draw the angle. And since we're negative, we're going clockwise. -3 pi over 4. It's right about there. So since we're dealing with secant, or cosine, the reciprocal of cosine, right? We're, let's see, 1, 2, 3 in the 3rd quadrant. All of our x's are negative. So this exact value is definitely going to be negative. We know that. It's going to be negative. And let's see, our reference angle is pi over 4. So the cosine of pi over 4, because again, I'm going to get cosine and then flip it, because I don't really know the secant of pi over 4 off the top of my head. The cosine of pi over 4 is √2/2. And we are negative. So -√2/2 would be the cosine of -3 pi over 4. But we're going to flip that since we're dealing with secant. So we actually have -2/√2. And if you do something called rationalize the denominator, you'll multiply by √2/√2. The √2's will become 2. The 2's will then cancel. And if you rationalize the denominator and fully simplify this, you're going to end up with -√2. Okay? So the secant of -3 pi over 4 is -√2, and we did that using the reciprocal identities. And again, if there's another way that you do it, that's totally cool, as long as you end up with -√2. So we're going to do a similar thing with cosecant here. Let's draw the angle. 11 pi over 6, wrapping all the way around, leaving me with a reference angle here of pi over 6. And let's see, in the 4th quadrant, so we're going to find, again, sine, and we're going to flip it. So what is the sine of 11 pi over 6? Well, I'm over here in the 4th quadrant. All my y's are negative. That means sine's definitely negative. And let's say we have a reference angle of pi over 6. So the sine of pi over 6 is 1/2. And since we're in the fourth quadrant, it's a -1/2. But since we're dealing with cosecant, we're going to flip that, and it's going to become -2. Y'all see how I did that? I did it kind of in my head a little bit quicker, but again, this is review. I'm expecting you know a little bit about this already, all right? And if you don't, I'll link a video right up there. But cosecant of 11 pi over 6 is -2, okay? Moving on to cotangent. We're going to rewrite this as cosine of pi over sine of pi, okay? That's what you can always do with cotangent and tangent, just the reciprocal of this, right? So let's see, what is the cosine of pi? Let's draw pi, that's all the way over here, okay? Cosine of pi would be -1 over, what is the sine of pi? 0, undefined. We cannot divide by 0, right? Undefined. So this exact value is actually undefined. U-N-D-E-F. I'm running out of room, so I'll just write undef. But it's undefined, right? Because we can't divide by 0. -1 over 0 is undefined. Clearly, this is undefined. So hopefully that made sense. All right, so number 4 says, given a circle of radius 12, part A, find the length of the arc subtended by a central angle of 75 degrees. So the length of an arc, basically I think of it just as a piece of the circumference of a circle, right? So let's say we have a circle here with radius 12. We're taking an arc, let's see, a central angle of 75 degrees would be about here. So this is the length of that arc, subtended by a central angle of 75 degrees. So as you can see, we have a piece of the circumference, and this piece, how much of the circumference, is dependent on that central angle. So here is 75 degrees. If we take a bigger angle, we have a bigger piece, and if we wrap all the way around, we just have the circumference. So that's exactly where this formula for arc length comes from. I have a video where I explain this in more detail. I'll link that. But we usually denote arc length as S, at least in the textbooks that I've seen, they call it S. And this just equals the radius of the circle times the central angle theta in radians. That angle has to be in radians. And if you replace theta with 2 pi, which is a full rotation, you get 2 pi r, which is just the formula for the circumference of a circle. So it does line up intuitively with circumference. So what are we being asked to find here? Let's see, we're given a central angle of 75 degrees. So really the only tricky thing we have to do, and it's really not even tricky, is to convert that 75 degrees to radians. So we take our 75 degrees, and again, the reason why is because this theta for this formula has to be in radians, okay? We take our 75 degrees and we multiply it by pi over 180, okay? How is this going to simplify? Let's see, common factor, definitely 5. I think 15 will work. 15 will go into 70, yeah, it's going to be 15. So it'll go into 75 5 times. So we have 5 pi, and then here it will go in 12. So this is our angle, 75 degrees, but it's now in radians. And we take this and we multiply it by the radius, which is 12. And this is going to simplify pretty nicely. Our 12s cancel. And what we're left with is 5 pi. So that is the length of the arc subtended by a central angle of 75 degrees with a circle with radius 12. So that's part A. Part B now says find the area of the sector formed by an angle of 11 pi over 12 radians. So the area of a sector is a similar thing as this arc length, but instead of a piece of the circumference, we're taking a piece of the area, right? So the area of a sector, let's see, 11 pi over 12 radians, so that's like almost half a rotation. So we're looking at the area of like this much of a circle. That's the area of a sector. So again, that area is determined by how far we go around the circle by our central angle, okay? And the formula for this is A equals 1/2 r squared theta. And if you replace theta with 2 pi, right, a full revolution, what do you get? The 2's cancel, you're left with pi r squared, which is the area of a circle. So it does intuitively, again, line up with area. Let's see, what are we being asked to find? Let's see, 11 pi over 12 radians, so that's going to be our angle. And we have our radius, so I think we're good to go. We can just plug into this formula. 1/2 12 squared times 11 pi over 12. And you could have wrote 144, but if you're slick, you'll see that one of these 12s will cancel. Right? Because this 12 is being divided. We have 12 times 12 here, so one of those can cancel with one of these guys. What else can cancel? A 2, let's see, 12 divided by 2, that gives us 6. So those can go, and we have a 6 So what are we left with? 6 times 11 times pi. 66 pi. And that is the area of the sector formed by an angle of 11 pi over 12 radians. And this is all with a circle with radius of 12. So hopefully this made sense. Number 5, here we go. I think this is a really good exam question because it really tests your knowledge of trigonometry in a few different ways. That's why I gave it a part A and a part B. But what we really need to know is our definitions for these trig functions. For example, sine theta, that's equal to y over r. Cosine theta equals x over r, etc. Those definitions, that's part of how we're going to find these exact values for the 5 remaining trig functions. We also need to know Pythagorean theorem. A squared plus b squared equals c squared. You probably all know that. But in this case, the legs of our triangles are x and y. So we have x squared plus y squared equals r squared, which is the hypotenuse. Same idea though, Pythagorean theorem. We also need to understand what this theta being in quadrant 2 tells us and what the hell this means, why we need this information. What if I change this to theta in quadrant 1? What would that change about the problem? This is what you should be thinking about and understanding conceptually, right? So using all that information, we're going to find the exact values of the 5 remaining trig functions. And I'm going to start with the definition. Like I said, sine theta equals y over r. So I already know that my y is 5, my r is 13. All I'm missing is the x. So we have x equals, who knows? We don't know yet. We're going to find that. Y equals 5. R equals 13. And wait a minute, how do we know that y is not negative 5 and r negative 13? Because that would still give us a positive, right? A negative over a negative. Well, because r is never negative. R is always positive, so that's how we know it. Duh. So if sine is positive, then y is definitely positive. So we just need to find the x now. So we're just going to jump into it. Pythagorean theorem. We got x squared plus 5 squared. And maybe you could have just wrote 25. That's totally cool too. All right, because this is going to give us x squared plus 25 equals 169. And maybe you could have noticed that this is actually one of those famous triangles, a 5, 12, 13 triangle. Comes up a lot, just like the 3, 4, 5 triangle does as well. There's kind of these common triangles we get used to. So this will become x squared plus 144. But when I square root both sides, what do I have to do when I square root? Plus or minus, right? Because I can square 12 or negative 12 and get 144. So I have x equals plus or minus 12. So wait a minute, I have 2 different values for x. This doesn't make sense, right? So this is really when this information comes into play, theta in quadrant 2. And this right here is why we need that information. If we were just given this, sine theta equals 5 over 13, it wouldn't be enough to find those 5 exact values. It wouldn't be enough because we wouldn't know, is x positive or negative? We don't know. Either way, it works out, right? But since theta is in quadrant 2 that's over here, x's, they're all negative over here. So it has to be negative 12. Let me quickly erase that. Negative 12. There we go. So that's what tells us whether our x is positive or negative. That's why we need that quadrant information. And just given that alone, we wouldn't have been able to know. Maybe we could be given this and then like the value of tangent, right? And use that information. But you get the idea. That alone won't tell us. We need to pay attention to that quadrant so that we can decide, is it positive or is it negative, right? So x is negative 12. That's pretty much the bulk of the work of this. If you know the definitions, I mean, we literally just copy down. Let's see. Well, first of all, which do we know right away? Which exact value do we know right away before even doing any of this? Cosecant, right? Because cosecant is the reciprocal of sine. We could have just copied that down right away. So cosecant theta, I just flipped this, 13 over 5. I just flipped sine, that's 13 over 5. Now we're going to use our definitions. Cosine is what? X over r, which means that cosine theta is negative 12 over 13. We have the reciprocal of cosine, that's secant. Secant theta, I can just flip cosine, I get negative 13 over 12. And maybe you're thinking, wait a minute, shouldn't the negative be in the denominator? Same thing, you can move it up, you can bring it down, you can move it out, you can flip it all around, you know what I mean? Flip it and reverse it, do all that stuff. Same thing, tangent theta equals what? Y over x, 5 over negative 12. I'm going to just write that as negative 5 over 12. Cotangent is just the reciprocal. And again, maybe you don't remember the definitions. Maybe you're like, I don't have these memorized. What the hell do I do? Well, hopefully you have some identities that you know. I don't know. Maybe sine and cosine would be enough. You could write tangent and sine over cosine and do that kind of simplifying and stuff. This is just the easiest way, in my opinion. But sure, there are other ways. Negative 12 over 5, the reciprocal of tangent. And I think we're good to go. These are the 5 exact values, the 5 remaining trig functions. Bam. All right, 5b. So here's another example where we're given some information and we're asked to find the exact values of the 5 remaining trig functions. So let's go ahead and start. Tangent theta equals y over x. That's the definition of tangent. So that means that y equals -1 and x equals 3, right? No, not necessarily, right? The problem with this is that -1 divided by 3 is the same thing as 1 divided by -3. So just by looking at this, I don't know whether my y is -1 and my x is 3, or my y is 1 and my x is -3. But I have this quadrant information. Theta is in quadrant 4. Quadrant 4 means what? Somewhere in there, that means my x is positive, my y is negative, right? So I needed that quadrant information, and actually in 5a, in the last example, we didn't use this quadrant information until after Pythagorean theorem. This time we used it right off the bat to determine if y was positive and x was negative, or if y was negative and x was positive, right? We had to find out which of those two cases we had. That's why we needed this quadrant information. If we didn't have this, we wouldn't be able to determine which was which, right? So quadrant 4, so we know that our y is negative, our x is positive. So we have y equals, let's see, y is negative. So -1, x equals positive 3. We need to find r. We need to find r, but we're still going to use Pythagorean theorem. So we have, let's see, 3 squared plus -1 squared equals r squared. That's going to give me 9. That's going to give me +1. That will combine to be a 10. I have 10 equals r squared. And when I square root both sides, do I need to plus or minus? No, because r is always positive, right? R is a distance. So I just take the principal root. Let's see, square root. I have r equals root 10. Can I bring anything out of that? Let's see, 2 or a 4. I don't think so. I think that's actually how I need to keep it. R equals root 10. Normally, if it were like, you know, if there was something I could bring out, I would write it as like 2 root 2 or something like that. If it were like square root of 8, I would. But I don't think I can do that here. So here we go. I'm at x, y, and r. And I can start listing out the exact values of these trig expressions. One thing I want to note, though, similarly as the last problem, we could have wrote out cotangent right away. If tangent is -1/3, cotangent is -3. So you always can at least find one. Even if you forget the whole process, if you remember that, you can get some partial credit. At least find one. So cotangent, we'll start with that one, equals -3. What else do I have? Sine. Whoops, I'm not sure why I wrote cotangent without a theta there. That's bad practice. Cotangent theta equals -3. Sine theta equals what? Let's see, y over r. -1 over root 10. Here's why we get to practice rationalizing our denominator. That is -root 10 over 10. I multiply the top and bottom by the square root of 10. Rationalizing the denominator. I have a video on it if you want to refresh yourself. Let's see, that means cosecant theta is root 10 over -1. So just -root 10. What else do we have left? Just cosine and secant. I'll write them over here to make sure I have room. Cosine theta is x over r. That is 3 over root 10. And after I rationalize the denominator, that's going to become 3 root 10 over 10. Okay? Cosine, and then we have secant as well. Secant theta equals root 10 over 3. Square root of 10 over 3. There we go. We have found the 5 remaining trig functions. We're good to go. That's it. All right, guys, number 6. Now we're going to graph some trig functions. This is really fun stuff. So let's go ahead and start with part A. It says graph the function, then state the amplitude, period, phase shift, if any, domain, and range of the function. So I'm actually going to state all that stuff first over here and then use that information to build the graph of this function. That's what I normally do to graph these guys, is get all that information first, then use that information to graph it. So let me put this paper down. I got my eraser handy just in case. I feel like this might be a little bit of a process, but we're going to get through it. So first I'm going to get amplitude. Amplitude is the absolute value of the number being multiplied out in front. So in this case, the absolute value of 2 is 2. Bam, there we go. Period. Next, I can get period. I'll denote this with a P. And you may use different letters, that's fine, or Greek letters or symbols, whatever you use, that's fine. Period, we're calling it P. Let's see, that is 2 pi divided by the number being multiplied out in front of the x. So there's no number, or you could think of it as a 1x, right? So 2 pi over 1 is just 2 pi. So our period is the same as the normal period. In other words, of the parent function. The period of the parent function is the same as the period of this function. So let's see, where are we at now? Phase shift, I'm going to write PS, real original here, phase shift. So where are we shifting? Well, that's determined by the addition or subtraction inside the parentheses, right? Directly involving the x here. So since we have plus pi over 3, we're shifting to the left pi over 3 unit. So minus pi over 3, shifting to the left pi over 3. And it doesn't ask us for it, I don't think, but I'm going to write also shifting down 1 unit. I'll write that, shifting down 1 unit, right? Because that's what this number out here, addition or subtraction out here, shifts up and down. So now we're ready to start building our graph. Let's see how ugly these lines are going to be. Not too bad, I guess. It's enough to work with. So what I like to do is get first the x points. There's going to be 5 points total, right? Normally sine starts at 0 and ends at 2 pi. At least on the x-axis, that's what we're focusing on. So we start at 0, end at 2 pi, but again, that's just our parent function. Now we have these shifts and transformations and stuff, so it's going to be a little bit different. Mainly, we're worried about this phase shift right now. What this does is it shifts it left pi over 3. So that means that instead of starting at 0 and going to 2 pi, we're going to start at negative pi over 3, okay? So I'll graph my first point here and label this negative pi over 3. And now, are we ending at 2 pi? No, because we shifted back by pi over 3, right? We shifted pi over 3 to the left. That means we're going to end at 2 pi minus pi over 3. 2 pi minus pi over 3. I can get a common denominator here. 6 pi over 3. That gives me 5 pi over 3. So I wrote out the steps for how I got this common denominator and combined this. For the rest, I may do a lot of math in my head. So again, hopefully you have that pencil and paper out. You've already done this on your own, or at least pausing the video and trying it, because I will skip some steps here in this video, just making it clear. I wrote this out. Hopefully you know how to find a common denominator and do the subtraction, because I'm about to just jump to it. Some quick maths here. 5 pi over 3. So let me erase this stuff out of the way. So I have my first point and my last point. Holy cow. I have my first point and my last point, so I need to get my middle point here, midpoint. How can I find that? How can I find that? Well, it's exactly halfway between this point and this point, so I can add these two and divide by 2, okay? So if I add negative pi over 3 to 5 pi over 3, I get 4 pi over 3. If I divide that by 2, I get 4 pi over 6, which is the same thing as 2 pi over 3. So this point here is actually 2 pi over 3, and I'm worried I may have to move these. Well, we'll see why in a second, but I may have to move these. That's why I got my eraser handy. We're going to now find what I like to call the quarter points. This I call the midpoint, I guess, half point. These are the quarter points, so we have points halfway between this midpoint and this first point, and this midpoint and this end point. Again, this is not formal terminology. I've just kind of developed my own, I've graphed hundreds of these, so I just kind of do it this way. I find it to be the easiest for me personally. So I'm going to do the same process. Add these two and divide by 2 to get this value, this x value here. So that becomes 7 pi over 3 divided by 2. That's 7 pi over 6. And same thing here. This becomes, when I add them, I get pi over 3. So this is pi over 6. So again, the scaling may not be perfect, but this is okay. We can work with this, all right? We have these 5 points. We know where we're starting and where we're ending. Now what I like to go through is the y value. So we're going to apply this vertical shift. So if we're going down 1 unit, then I'm going down to here. And this is our new midline. That's what this vertical shift does. It changes the line we're oscillating about. Normally with just y equals sine x, we're oscillating about the x-axis or the line y equals 0. Okay? This addition or subtraction out here, it changes that line we're oscillating about. So now we're oscillating about the line y equals -1. Okay? Y equals -1. And again, this is why I may have to erase this stuff, because I think it's going to get in the way of my graph down here. So since our amplitude is 2, the amplitude I think of as a distance. And it's the distance from the midline to the maximum, and also the distance from the midline to the minimum. So since our amplitude is 2, and our midline is y equals -1, we're going up to +1 and down to -3. So this is our maximum, this is our minimum, up to positive 1 down to negative 3. So I am going to have to move a lot of this stuff. Let's see, negative pi over 3, that can go here. I may just move it all up. Pi over 6. Let's see, 2 pi over 3. And these are referring, again, to these x values. 7 pi over 6. 5 pi over 3. All right, good. I moved it up a little. I think that gives us enough room. So let's see, we can plot our first point. Where does sine normally start? At the midline. So we're going to start at our starting point at the midline. So this is our first point. We'd say it's negative pi over 3, comma, negative 1, right? So what is our next point? Where does sine normally go? It first starts at a midline and goes up to its maximum. So we're doing the same thing still. The only way that would change is if we had some kind of reflection. Then we would go down to the minimum first, if this was like a negative, right? So that's where that reflection would come into play. But I literally just complete this process. Up, back down to the midline, now down to the minimum, and now back up to the midline. Bam. And that is the graph of one full period, one full cycle of this function right here. Hopefully the way I approached it makes sense. Again, if the way you do it is slightly different, that's okay, as long as you get the same result, which is a beautiful, perfect, stunning graph of this function. Hopefully that makes sense. Let's dive into part B and part C. Psych, I almost forgot. Domain and range. What is the domain of this function? All real numbers. We can plug any real number into this function. There's no issues. With sine and cosine, there's pretty much never going to be issues. So our domain is all real numbers. I like to write it as all the numbers between negative infinity and infinity, which is all of them, all right? But what is our range? Well, we can see it from the graph. The minimum value is negative 3, the maximum is 1. So our range is from negative 3 to 1, and we do include those values. Pretty straightforward, hopefully, but yeah, sorry, I almost forgot that. All right, 6b, we got another example. We're going to graph. Let's go ahead and start. What's the amplitude of this function? Remember, the amplitude is the absolute value of the number out in front here. It may look like there's not a number, but there is. This is sort of like a little negative 1 hanging out in front being multiplied to this function. So absolute value of negative 1 is just 1. So it turns out our amplitude is actually the same as the parent function, as just y equals cosine x. What else are we going to find? Our period is 2 pi divided by the number out in front of the x that's being multiplied. So 2 pi divided by 3, that's the period. So that's how long it's going to take to do one full revolution. We're going to see that when we graph it. Phase shift, I'm going to write that as PS. Phase shift, is it to the right by pi over 2? This is where you have to be real careful, and this is why I put this example in, because our phase shift is not just that number if there's some number being multiplied out here. And the way I was taught, and I'm going to erase this in a second, but I was taught to rewrite this as minus cosine and factor the 3 out. Factor the 3 out, so you're left with x minus pi over 6. And the plus 1 is still out in front. This is actually the same thing as that. This is how I was taught, because then you can directly see that this is the phase shift. And I break that down a little more in one of my graphing trig functions videos. But our phase shift is to the right by pi over 6, not pi over 2. So I'm going to write it as plus pi over 6 because we're going to the right. We're shifting to the right. What else can we write? Well, there's a negative out in front, so we can write reflecting. And where is it reflecting? I like to think of it as reflecting over midline. Reflecting over the midline. And we're going to see how that works out when we graph it, but I like thinking of it this way. And then we have shifting up 1 unit. So I'll write an up arrow 1 unit. I think that's all the information we need for now. We'll get the domain and range at the end. Let me get this out of the way, but hopefully that makes sense. I like doing that little factoring out the number out in front. You could also just take this number and divide it by that number. I think there's like a formula they give students involving like omega or some Greek letter stuff, but that's how I think of it. That works, but the phase shift is definitely to the right, pi over 6, okay? So let's see how bad this graph is going to look. Whoa. Not bad. Okay, so let's graph this thing. We got our first point, and that's dependent on our phase shift here. We're shifting to the right by pi over 6. So that means our first point, instead of being at 0 like it normally is going to be at pi over 6 here. So I'm going to write this here. I don't know where this pi over 6 is going to end up. I'm going to write it way down here. Hopefully I don't have to erase everything this time. So pi over 6, and we're going a distance, right? How long is it going to take to do a full cycle? Well, that's our period. So we're going all the way up until 2 pi over 3 plus pi over 6. I'll write this out this time. Pi over 6. 2 pi over 3 is 4 pi over 6. And that's going to become 5 pi over 6. So that is our last point. We're starting at pi over 6, and we're going to 5 pi over 6, okay? Hopefully that makes sense. I took the first point, I added the period, and that gave me the last point, just like the last example. That's what I always do. So 5 pi over 6. Now I can split this up directly in the middle, and I think we can even notice a pattern here. This is kind of a cool example because we have pi over 6. If we add the 2 and divide by 2, we get 6 pi over 6 divided by 2. That is what? Pi over 2, or 3 pi over 6. So we can think of this as like 1 pi over 6. We have 3 pi over 6, 5 pi over 6. So this is going to be 2, this is going to be 4, right? There's a little pattern. 1, 2, 3, 4, 5. They divide up pretty nice and even. So let's see. I'm going to follow that pattern. Pi over 2. And if you didn't notice the pattern, it's all good. You can just add these 2, divide by 2, add these 2, divide by 2. This is going to be pi over 3 because it's 2 pi over 6, 3 pi over 6, 4 pi over 6. That's 2 pi over 3. So we have all our x values that we need. Let's see what we can do next. We're probably going to next go ahead and graph the midline. So since we're shifting up 1 unit, our midline is moving from the line y equals 0 to the line y equals 1. So I'm going to draw this 1 here, do a little dotted line because that's what we're oscillating about. And our first point, now let's see if we can go ahead and plot our first point. Cosine normally starts, maybe I'll do a little graph off to the side here. We normally start at our maximum. Then we go down to the midline. Then we go down to the minimum. Then we go back to the midline. Then we go up to the maximum, okay? So normally we're going to start at our maximum. And since our amplitude is 1, our maximum is going to be 1 plus 1. That gives us 2. Our minimum is going to be 0, okay? That's 0, of course. But we have this reflection. We have this reflection, which means that instead of starting at our maximum, we're going to reflect over this midline, and we're going to start at the minimum. So our first point is actually here. Well, not there at 0, 0. Here at pi over 6, 0. Sorry about that. Almost made a big boo-boo. Pi over 6, 0. So we're starting here, okay? Then we're going up to the midline, but following that same pattern. Midline. Then we're going to go up, let's see, where do we go next? To the maximum, then back to the midline, then down to the minimum. Bam, 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 something like that. This is not my best work, guys. I hope you get the idea from this. So that's the graph. Let's see, let's make sure I did everything right. I included the amplitude, the period's good, phase shift, we did shift to the right. Reflecting, we did do the reflection, we shifted up 1 unit. Yeah, we're good to go. This is the graph. Now, what's the domain? Well, we're not looking at the domain of just this period. We're looking at the domain in general, which is going to be all real numbers, negative infinity to infinity. That's kind of a gimme. It's an easy question. The range is the part that takes a little bit of work, but still not much. We're just looking at the range of y values. Our minimum is at 0, maximum at 2, 0 to 2. Bam. That simple. Hopefully this helps. All right, here's part C. This is the last trig function we're going to graph in this video. And it's a tangent function, which a lot of people seem to be scared of, but there's no reason to be scared. We're going to just jump into it just like we do with sine and cosine. So first, let's look at our amplitude. The amplitude is still just the absolute value of that number that's chilling out there in front. So it's still 3. And by the way, I've heard some of my students say the amplitude doesn't matter with tangent, cotangent. They still just go off to infinity and negative infinity. Well, it does matter. It does change the graph. It's just not that drastic of a change like it is with sine and cosine. But it does matter. The amplitude matters, okay? Hurting the amplitude's feelings by saying it doesn't matter. Period. What is the period? Well, instead of 2 pi divided by that number, we do pi divided by that number, which is 1. So pi over 1, pi. So our period is pi, which is the same as the period of y equals tangent x, our parent function, right? Period, let's see, not period shift, phase shift, okay? Phase shift, we are shifting to the right by pi over 4. Pretty straightforward. There's nothing we need to factor out or divide by or anything like that. Shifting to the right by pi over 4 units. All right, what else can we do here? There's no vertical shifts, there's no reflections. I think we're good to go. I think this is the information we need to start, whoa, what happened there? To start graphing this guy. All right, let's see. So normally we go from negative pi over 2 to pi over 2, but now we have this phase shift. We've shifted to the right by pi over 4. So instead of starting at negative pi over 2, we're going to start at negative pi over 2 plus pi over 4, which I believe is negative pi over 4. So I'm going to write right there as negative pi over 4. And remember, our first point is actually an asymptote. So it's a dotted line all the way down. Bam, asymptote on point. And then we're going to get our last point by doing what? The same thing as sine and cosine. Same thing. We just add the period. So period plus negative pi over 4. That gives us the 3 pi over 4. Let's see. Right about here, I think maybe I should do. I'm trying to get the spacing perfect. I don't think it's going to be perfect no matter what. So let's dotted line. That's an asymptote again. Now we divide it up. Halfway between is what? 3 pi over 4 plus negative pi over 4, that gives me 2 pi over 4, which is pi over 2. And divide that by 2. Okay, pi over 4. Oh, I could have probably seen that. We have a negative 1, 0, 1, 2, 3. That's where our 5 points come from. So exactly in the middle is going to be pi over 4. This is going to be 0. This is going to be 2 pi over 4, which is pi over 2. I see it now. Pi over 2. This here is pi over 4. And let's see, what are we worried about next? We have all our points. This is 0 clearly. Let's see, we haven't shifted up or down at all. So normally when we graph this guy, we go from, let's see, we have a point up here at 1 and a point down here at negative 1. But that's what this amplitude does, is it stretches these points. So now we're going to have points at 3 and negative 3, okay? And normally this point is at, let's see, pi over 4, 1. So this point here normally is at that point 1, but now it's at 3 because of that stretch. So that's what the amplitude does, is it stretches it, and now we're down here. But other than that, it looks very similar. So yeah, the stretch, in the case of sine and cosine, that amplitude changes the range of the function. In this case, it doesn't change the range. So maybe from that perspective, you could say it doesn't matter, but it still matters by the way the graph looks. I mean, you could stretch the hell out of this thing and completely change the way it looks. But as far as the range is concerned, it doesn't matter. So I guess I see that point of view from my students. I didn't mean to call anybody out. Let's see, we're going all the way toward that asymptote forever and ever. Same thing here. And there we go. It's a beautiful graph of this tangent function. And what do we have left? Domain and range. So domain, range. I'm going to probably need more room for the domain. We know the range goes from negative infinity to infinity. The domain is kind of the tricky part of this function. How are we going to find the domain? Well, normally we have asymptotes at negative pi over 2, pi over 2. So basically it's pi over 2 plus or minus any multiple of pi. But now we have, let's see, instead of pi over 2, we have 3 pi over 4. So the domain, I'm going to rewrite it down here. And again, for the level of like trig and pre-cal, I don't know if you'll be expected to know how to find a domain like this. It's a little bit tougher to think about. But basically what I'm thinking about is that we have an asymptote here, and if we add or subtract any multiple of pi to this, we get another asymptote. So we're going to say probably the domain is all real numbers such that x is not, what can't x be? It can't be negative pi over 4. It can't be 3 pi over 4. It can't be, and we can keep add or subtracting any multiple of pi. So I'm going to write cannot be 3 pi over 4 plus pi k, where k is an integer. K belongs to the set of integers. So again, this may be over your head. It may be a little complex for the level of trig and pre-cal. That's okay. If you understand the idea that these asymptotes appear, you know, in every pi units, right? I add pi. If I add 2 pi, there's another asymptote, 3 pi. If you understand that concept, then you're good to go. As far as writing this out, don't stress out too much. Ask your instructor what they expect you to do with questions like this. But hopefully this helped. All right, guys, so question number 7 says, sketch the unit circle from scratch. And then I give a hint, and I say, remember that the unit circle comes from taking the special triangles and placing them inside of a circle with radius 1, etc., etc. I realized after typing this up that this probably isn't the best hint to give, and the reason why is because this is the way I conceptualize and think of the unit circle, and it may be good to explain something or to offer some explanation from my perspective, but really the point of this question was to encourage you to think about the unit circle and really all of these concepts in trigonometry in your own way, right? And what I recommend doing is setting aside 15 minutes to an hour, pulling out a pencil and a few sheets of paper and really just writing things down. Almost treat it like a journal entry. Write out your thoughts, write out the concepts, write out what you know, write out what you have questions about. I really think you'll get a lot out of it. That's what I still do in my math classes today, and I do get a lot out of it as well, because what I get from it is a lot of times I make connections. I understand new things in new ways and in my own way, because I wrote it out and came up with it myself. And sometimes I realize that there are holes in my thinking, there are misconceptions I have, and I'm able to write out questions and bring them to my instructor's office hours or ask them on Math Stack Exchange or wherever it may be. Text my buddy John from Epic Math Time, you know what I mean? Whatever it may be, I come up with these misconceptions and I come up with questions so I can get them answered and, you know, understand these things to a deeper level. And that was really the point of this question number 7, was to encourage you to do that. So maybe the wording of the question, you know, maybe I missed the mark in that aspect, but that was really the goal of this. So if you want to see me draw out the unit circle in my own way, then I have a video where I do exactly that, and I'll link it. It'll pop up right above here. But that was the goal of this question, was to get you to really sit down and think about these concepts and write things out and understand all this stuff in your own way, right? If we get to the same answer, then it's good. As long as you did it in your own way, that's really what's going to help you. So that's all for this video. We made it through final exam review part 2. If you made it this far, thank you so much for watching. I really hope this helped you. I really do. And if it did, share it with your classmates, with your friends, hit like, let me know in the comments below, subscribe, but most importantly, keep flexing those brain muscles. See y'all later.